Hey, welcome. Nice to see so many people here, really great. All right, I'm Nicole. I'm a independent software developer and software development coach. And I would like to um, give you a short experience report of my way of introducing event sourcing into Node.js, or my attempt at least. So, okay, what are you going to see or hear here in this talk? First, I will give a bit of motivation. Why would we do something like event sourcing? By the way, I'm not talking about this event sourcing in the browser thing, but about the event sourcing in the backend, in case somebody gets confused here. So I will give you a little intro to what it actually means, show you how I started implementing it, how I failed with it, then why I failed, and how I improved on that. Okay, so why event sourcing, or how did this all begin? I'm also organizing a conference. The conference is called Socrates. This is the logo, also here. And in 2015, so last year, we had the registration. We are writing the software for the conference registration ourselves, and this is also a software that is a platform for software craftsmanship, so it does a lot more than just the conference registration, but we added this on top. And our registration model is a two-phase registration. You might know this from Eventbrite or other sites. So first you get a reservation, and then you can take your time entering your data and everything that's required, and then you submit it and you get your registration if this happens in a time frame of 30 minutes or less. Otherwise, your reservation will be discarded and somebody else can pick it up. So, what happened last year during the reservation? We ran into a bug and 11 people entered the reservation phase, and although they submitted their registration within the time frame, they couldn't register, but instead saw this: subscription is not yet available, or all spots are taken. Now, this is a big bummer for a conference registration. 2 or 3 users came back to us and complained, and so we could sort them out. But what about the others? We had no idea who they were. The reservation token only contained the session ID of the browser, which is not exactly helpful to identify somebody. And also it was deleted after 30 minutes, because that's how this process was supposed to work. Free up the spot after 30 minutes. So we had no idea who those people were that made the registrations, and probably they were pretty disappointed that it didn't work out, although they didn't make any mistakes in the process. Okay, so I was asking myself, how can this actually be improved? How can we at least learn about the people who entered in the reservation phase? At that time, I learned about event sourcing. Somebody also uses to call this "don't drop data", because that's exactly what you do. You stop dropping the data in event sourcing. And that's a really cool thing. And so I thought you might be interested in hearing a little bit about it. So in a classical approach application, usually you have a relational database. And this relational database only contains the current state of your system. So you don't have any history. You don't know what it was like previously. You don't know when it changed or even why it changed. And this usually makes you blind for information from the past. You can't see it anymore. And the idea behind event sourcing is just to record everything that happened and also the reason for it to happen. Because if some person's address in an address registration system changes, that might be because the person moved or because there was a typo in the address, which might make a huge difference business-wise, how to react to that or whatever. So if you now have all the lists of everything that happens, then you can derive the current state of your application by just going through the list and applying all of those changes one after the other. You can imagine this like your bank account. Usually you have a list of all the deposits and all the withdrawals over time. And if you start from 0 and you recalculate and add and withdraw all those changes, then you will get in the end to your current amount that you have in your bank account. And this is basically also how event sourcing works. I will give you a bit more detailed explanation of it, how it works technically. So imagine there's a person going to a web browser, and what they do is emit a command. So they say, I want this and that to happen. For example, if the person is an administrator of our conference registration site, she might want to say, set the ticket quota. I want so many tickets to be sold for the conference. Then the command processor emits an event. The command is different from the event. In this case, the event, and the event is stored in this long list in our event store. In this case, if the administrator says, set the ticket quota, the response will be, the ticket quota was set. And there is no way to argue about it, because if the administrator says, now we're selling 200 tickets, then we're selling 200 tickets. Nothing about it. After that, once the event got stored in the event store, it will be sent out to the so-called read models, and they are used to drive the website. So they provide information derived from the events so that it's very easy for the website to consume and to display. Ideally, it should be a one-to-one relationship, so there should not be much work to be done to go from the read model to the website. It's very important in this model that this event store actually is the source of truth. So everything must go to the event store first before it gets radiated out back into the website, because if the system crashes or whatever, we need to have this record to get back to, because once we told the user, hey, you got this ticket, and then later on we crashed, just in this space in between, and then we lost the information again, that's a bit stupid. So the event store is our system of record, and we first submit everything there and then distribute it out again. So, but what if there's some other command coming into our command processor? For example, the user says, hey, I want to book a ticket. So this is not a single response that we can give here. There might be multiple things that could happen. For example, the ticket is booked, or maybe the conference is already sold out, or maybe the person already bought a ticket and they can only buy one in our system. So what we do need is another way of helping the command processor decide. And that's what is called a write model, because it's for the writing of the events. And this needs to be also filled from the event store, but this needs to be synchronous, because we need to be able to reflect the actual current state of the event list in this write model at any given time. And then the command processor can go and ask the write model, and if the write model then says no spaces left, then the command processor can decide, okay, I need to submit an event stating it was sold out. And then also it gets radiated to the read model and then to the website, so the user gets the appropriate reply to his ticket request. Okay, when we look at this in a very standard scenario, we often have an application server in the backend, say in Java or whatever backend language you favor. And we have the read model and the write model in the application server state, and they get updated incrementally by each event that comes in. It gets folded into the models, and then the model is up to date again. As I said, it's very important, the write models must be updated synchronously, and the read model can be synchronous, can also be asynchronous. That's not that important, because we already have a delay because of the web, and so it's not that important. So what did we do? Our application is written in Node.js, and so we decided, okay, Node.js works a little bit differently, but we still give it a try. We run an experiment with event sourcing, And we use this only for the registration part. So the rest of the application is like standard Node.js stuff. And we need to adhere to one constraint, that is no overbookings, because this conference, the tickets match to a hotel room, so we cannot do overbookings. For other conferences, it's not that much of a problem, but for ours, we need to, make sure that we just give out the exact number of tickets. So keeping that in mind, we started implementing this, or I in that case, and it works like this. First, we have a long list of the event constants, one constant for each event. I talk you through the ticket quota setting thing because it's a bit easier, so we can go over it a bit more quickly. And first we say, okay, this is the constant. Then we also have a constructor. We give it the new quota, and then we get an object just to make sure that our events are formed always uniformly. So we create this function. And then for the command, where we call the set quota, well, what do? We construct the appropriate event and hand this back. If we had a decision phase, like I showed with the ticket booking, that would happen in here, in this set quota command down here. But for this example, it's very simple. Command in, event out. So how does the read model look like for this? First, we start out with an undefined quota because we don't know anything. And on creation of the read model, we get the list of events that have already been seen in the system. So our system might be running for a year or so, and now we do a reboot, and the system comes up, creates the read model, and all the events from the past year are passed into the constructor, and they are processed there. So what do we do in processing them? Basically, we reduce over them and to get to the new quota value. And how do we reduce over them? So these events can be anything, but for this one read model, we need to pick out just those that are interesting to us. So we look specifically for the room quota was set events, and if we find one of those, we pick the new value, otherwise we keep going with the old value. And now if a website comes and asks, so how many, what is the quota set to actually right now, then we can just return this value. We don't have to do any fancy calculations or anything. This is really fast. So, the magic day came. This year, we opened the registration with the new event sourcing stuff. The registration began, but nobody registered. What was going on? So in order to understand this, we need to step back a little and we need to have a little look at Node.js and how it works. In Node.js, you have this nice internet, and you have a request coming in, and everybody knows Node.js is single-threaded. So the request comes in, it gets processed, and the result gets returned again. So everybody also says, ooh, single-threaded is very bad because it blocks everything, so let's do a callback. But a callback by itself doesn't make anything parallel or whatever. It is still single-threaded because you just pass in a function and you call the function inside. So what? Okay, still single-threaded. But now, if you do async I/O, then this is a point where it breaks and where Node.js, if it encounters an asynchronous call, it will put your call or your processing thing that's currently going on, it puts it on hold, and now it can accept more calls. So if you go to the database, all of a sudden you have parallelism in the system. This is how Node.js is designed. This is desirable to have this, because otherwise each request would take as long as it takes to compute it, and that wouldn't be a good thing. But this is very important, and we need to know this and to work with this. So the other thing is we use the MongoDB, which is quite nice, I think, because it's also JavaScript. But MongoDB is very simplistic. So you have no transactions and you have no optimistic locking. what we did was also for the rest of the application, we implemented optimistic locking ourselves. And this is how it goes. So if somebody wants to book a ticket, we would load all the existing tickets from the ticket database and check whether a booking is already possible, is still possible. If no, okay, that's easy. We give an error message back to the user. But if yes, we would update the tickets, and then we would store the tickets in the database. Well, really? Would that work well? I don't think so. Because here, in this loading, this is happening asynchronously. And now, this is the cutting point. So it might be the case that somebody else also updates the database. So here, you will get a race condition and a conflict. So what we needed to do about this is to reload everything from the database again, check whether there was a conflict, and then write it out. Luckily, MongoDB provides an atomic operation for this, so this was really safe, and we could do this. Then what to do about if we had a conflict? Well, we thought, okay, let's try it all over again, and eventually it will sort itself out. So what we did in general for the general website thing is to use the same data and to start the process all over again, which works fine for the rest of the application. So we thought, let's do this with the event sourcing stuff as well, and it will sort itself out. Perfect. Okay, so what was the architecture, overall architecture of our Node.js application? We had this standard loop. A request would come in, would go to the database, and then return a value, or a result, a response. And we didn't keep anything in memory between those requests. So, I mean, you have a little bit of caching from request, of course, from require, sorry. But we didn't exploit this. We didn't actually put state into our required objects in order to keep track of something. So the application by itself didn't have any state at that time. So if we now think about what I told you about event sourcing previously, there I said usually you have these read and write models in memory and you update them incrementally. And now the question was, how do we model this in our Node.js application? And I talked to a couple of people, and we estimated like, oh, we might have a couple hundred events altogether for this. And so, well, let's try it. Let's hydrate the read and write models on each request. So a user would come in, would go to the database, load all of the event store, would process all of the event store, we would calculate the answer, persist the new event, send out the answer, and forget about everything. And then the next user, we would do the same thing. Naive approach. Like Jeremy said, do the simplest thing that can possibly work. Well, possibly. There you go. Okay, now back to our registration. I said it didn't happen. Nobody registered. And now the question is, why? So initially I mentioned we had this two-phase registration, first the reservation and then the actual registration. And what happened was the first user came in, went to the database, and so the moment they touched the database, we got this parallelization. So we had more users come in. And the conference is quite popular by now, so we had a lot more users come in. And they would also read from the database. And the first user could persist her reservation because there was no conflict here. Everything went well because it was the first who tried to save. And then the subsequent users produced conflicts because the first user had already saved and they were reading this in parallel, and so the version counter we had implemented didn't match anymore. So we said, okay, let's try this again with the same data. And so they retried. The same data went in, they went to the database, they hydrated all the read models, all the write models, they decided what to do with the ticket, they went to the database, and because this was so slow, and this opened up such a large window of time where other parallel users could come in, they also got conflicts. And then they retried again, and it was slow again, and so on. So it was a very nice exponential curve of blockings. And yeah, the slow hydrating on read and this huge number of parallel requests due to this big window led to a self-propelling disaster in the end. After 25 minutes into the registration, I shut down the server, and nobody had been able to register. Now, that was a bit of a bummer to all of us, and we needed to get our act together a bit and recover from this. And luckily, I found a person who's very proficient with event sourcing as well as Node.js, and he helped me a tremendous lot to sort this out. And this is what we went along with. So the first thing was that we discovered that hydrating those models took longer than we expected, especially since we had so many conflicts. We would get many more events than we had initially thought of, because each conflict would produce an event. Of course, we're doing event sourcing. We record everything that happens in our system. So we were thinking, okay, we must give up this idea of having a clean, stateless application. We need to cache actually our read and write models. And this is how this goes. In order to get the cached event store from the system, first we go to the cache and see if it's already there. If it's not there, we get it from the database. And what happens here, or what might happen here, if we go to the database? Again, we have parallelism. So what could happen is that in the meantime, somebody else already put the event store with some events into the cache. And so what we need to do inside this callback here, because inside this callback we are safe. We are just single-threaded again. There's no parallelism going on somewhere in between. It's only on those like crack lines of where you go to the database and stuff. So the first thing we need to do is we need to look into the cache again to see if it has got into the cache in the meantime while we were fetching it. And if we find it in the cache, yeah, we need to use that. If not, we can eventually put it into the cache and return it, and that's fine. So we know we were the first ones, and that all is well. So for the read model, it's basically the same. We first look into the cache, then we try to get the cached event store, because we need that for the events on startup of the read model. We look into the cache again, because this cached event store can also be parallelized. And then we can create the read model, give it all the events, so it can process them like I showed you before. We can put the read model into the cache, and we're fine. So the second problem, parallelization leads to write conflicts. So we must eliminate the parallelization. The caching already also had parallelization problems. That was the first problem. We need to address two more situations where parallelization can happen, and we need to eliminate them. The first thing is, I showed you how true event sourcing works. So true event sourcing says you need to persist your event to the event store before you distribute it out to the read models and write models. Well, okay, this is like the theory of event sourcing. We decided, because we cannot do this, because the moment we touch the event store, we will be subject to parallelization, so this is a big danger. And after parallelization, we cannot update our write model synchronously anymore. So we are doomed as soon as we touch the database. So we made a decision to go against the true, real thing. We decided to first send the events to the models to let the models incrementally update. And then only we would store it to the database, because we need to make sure that this is the last thing that happens. Like I said, this in order to avoid the parallelization. This is very important. Another thing is, so we have the loading of the event store, we have some calculations in between, then we have the update of the models, and now in the end we save the event store. But what if here in between I go to the database and I get some data? As I said, we only event sourced the registration part. But what if I want to load some member information from the database? Because the members are stored like in a traditional way. This will also cause parallelization here. So we have to make sure that this doesn't happen. We need to reorder, go through all our code and reorder everything to make sure that all the database accesses have happened before we actually fetch the event store from the cache and before we work with it. Because only after all of the database accesses happened, we know we are safe and we can, there is no parallelization going on. So what is the benefit of working in this way? Well, the benefit is we have synchronous code between the loading and the updating of the event store. And so there is no possibility for write conflicts anymore. And we can even save unconditionally. We could kick out our version counter and our conflict checking business going on, because we just always only write to the event store. And so the event store for us now has become more like a backup of the events, rather than like the single source of truth. There is a trade-off to this, of course. Now that we have state, we cannot run Node.js process in parallel, and this is like the #1 go-to when you want to scale your application, but we cannot do this anymore, so there is no way of scaling once this runs out of hand, or we need to think about stripping out the part of the application and just have this run in isolation, and the other parts can scale, but this part here cannot be scaled at all. So, what did I want to tell you? Event sourcing is a good way to avoid loss of information, so you can keep track of what actually went on in your system, and you can later come back and you can also implement new features on top of the data that you have stored, although you don't need it right now. It works well in Node.js if you take care of two things: avoid long load times and also avoid parallelization in your application, because otherwise you get race condition problems. And that's all I wanted to tell you. Thanks very much. Thank you. The slides are online at GitHub. The whole code base I was talking about is also open source, so you can go and have a look at it and play around with it if you want. You can get in touch with me if you want, and if you have any questions, go grab me. I also have stickers of the conference. If you have become curious by now what conference this actually is I was talking about, go grab a sticker from me and see you around. Thanks.